Welcome to the Wales Tech Week cluster stage, supported by CSconnected, representing the world's first compound semiconductor cluster based here in Wales. We hear about clusters all the time, but what is a cluster? In general terms, a cluster refers to a group of things that have something in common and are usually closely located. During the COVID pandemic, we have often heard the term used to describe local outbreaks of coronavirus infections, which has obvious negative connotations for the term cluster. But in a business and technology context, clusters are seen as having a major impact on innovation, productivity, and economic growth. The outbreak of the Industrial Revolution in the UK during the 18th and 19th centuries could be seen as an early example of a cluster. We then saw many examples of concentrations of new industrial sectors, from automotive, centered around Detroit, to technology born in Silicon Valley. Not so far away from us here today, Hay-on-Wye serves as a good example of a cluster outbreak with its high concentration of bookshops. One may question whether Hay-on-Wye is a good location to set up a bookshop when there is so much competition, but once a cluster reaches a critical mass, it becomes the go-to location for attracting talent, customers, and other associated resources. Business clusters tend to be unplanned. Most clusters form around a central point of expertise or innovation. Detroit only became known as Motor City following Henry Ford's pioneering use of assembly lines, and Silicon Valley was born out of innovative technologies emerging from the likes of Stanford University. The compound semiconductor cluster here in Wales was formed around solid research facilities at Cardiff and Swansea universities, and key anchor companies such as IQE, Newport Wafer Fab, Microchip, and SPTS. Like the Hay-on-Wye example, most clusters comprise of entities that compete with each other, whilst sharing some common attributes. A unique feature of the compound semiconductor cluster is that it has evolved from being a random group of entities into a semi-planned cluster with the addition of organisations such as Compound Semiconductor Centre and the CSA Catapult, along with new businesses including Rockley Photonics and MicroLink devices. The result is an enhanced cluster, which is more of a community that is characterised by multiple collaborations and shared resources, creating a unique and innovative ecosystem. Wales is a small concentrated country which lends itself to supporting clusters, and it is a pleasure for the CSconnected Compound Semiconductor Cluster to be joined during Wales Tech Week by other clusters forming around technologies such as resilience and cybersecurity, blockchain, and many, many more. I hope the cluster stage provides you with inspiration and opportunities. Well, first of all, welcome back to day 2 of Wales Tech Week. We had a pretty full day yesterday on the Photonics cluster stage, which leads neatly into the compound semiconductor activities that we'll be talking about today. So I'll start by just running through some introductions. I'll be very brief, and then we have a great lineup of speakers. We'll be going over to Andy Sellars of the CSA Catapult, followed by Paul Meredith from Swansea University and Peter Smowton from Cardiff University, and then a little later, after a break, we'll be introducing some of the industry partners, and this afternoon we'll be going on to some of the educational opportunities for anyone wanting to join or find out more about how to start a career and take up the opportunities that we have within the cluster. So I'll start sharing my screen now just to give a very brief overview. Okay, so say welcome to CSconnected. CSconnected is the umbrella term for the activities for various elements of the cluster. Just wanted to touch on how fast-moving the semiconductor industry is. The first integrated circuit, which was a combination of transistors. That transistors really go back to the 1940s, 1950s. But the real breakthrough came when Intel managed to integrate a number of transistors into a single circuit. And the first commercial device was produced in 1971, containing about 2,500 transistors, which was something of a breakthrough at the time. But over the intervening 50 years or so, we managed now to produce something like 26 to 30 billion transistors on a single chip, or devices on a single chip. And I can't think of many other, if any other industry that's really progressed at the same rate over that period. It really is a fast-moving industry. And a lot of it comes down to materials. We adopted the silicon age back in the 1960s and 70s, and that really ushered in the digital revolution. And we're now moving into a whole range of new and advanced technologies around power, energy, and around connectivity, healthcare technologies, and so on. And a lot of these are not further enabled by continuing shrinking that has really brought the semiconductor industry as it stands at the moment to where it is today. But it's actually by changing the materials, atomically engineering what we have in order to increase the performance and to make use of sensing applications that use optics, photonics, and so on, which was yesterday's theme. And really, if you look at humanity, we've always been defined by the materials that were important of a certain age. So from the Stone Age to the Bronze Age and Iron Age and so on, the tools that were used to help evolution really were what stood out as various eras in human evolution. Hopefully one day we'll look back on this as being the semiconductor age. It's all about the materials and the atomic engineering, and it really comes down to these silicon, compound semiconductor materials such as gallium, indium, arsenic, aluminium, nitrogen, and so on, combined in different ways at the atomic level. But that's really at the start of a really complex and fragmented series of supply chains that feed into the end products that we're all familiar with and we all know and love, from electric vehicles through to autonomous drive vehicles, robotics, energy, sensing, and connectivity. So we're all used to the products that compound semiconductors go into, but the route that they take in order to get to the final products is pretty convoluted. And it's pretty complex. We have a number of large-scale global systems, if you like, and this has really led to issues over recent years, in particular with trade wars between various countries, and also the COVID pandemic, which has disrupted a number of these supply chains. But if we look at things like ultra-fast broadband, a lot of the components are produced in the UK. We own a lot of the IP relating to the technologies involved in optoelectronic communications, particularly the lasers and the detectors that are used at the ends of optical fibers or fiber broadband. That gets shipped around the world, and then from North America and other parts of Asia, often ends up in places like China. And then, ironically, we buy back our own technology with much more enhanced value as it goes through the supply chain that we use in our ultra-fast broadband systems. And if you look at the history of where semiconductors are produced, California was the real home of the semiconductor industry in Silicon Valley back in the 1960s and 70s. But a lot of that has migrated over to Asia, with Japan, Korea, and Taiwan playing an even more dominant role in recent years. But in Europe, we have 4 clusters around Grenoble, Leuven, Dresden, and Eindhoven, and now a 5th cluster, and one that actually could be determined as the first, concentrating on compound semiconductors and not just silicon alone. So it's a real opportunity. Already we've heard mention of organizations in the cluster, IQE, Newport Wafer Fab, SPTS, and Microchip, along with the compound semiconductor applications Catapult and CSC. And then, of course, supported by the universities, Cardiff and Swansea. And we have a complete ecosystem that really goes to make up what we have today within the region. Although we've had a cluster for between 30 and 40 years, it's really only over the last 5 or 6 years that it's really been starting to work as one. What identifies it as unique is it's effectively an open source, what's called a foundry model, which means that different elements of the cluster work on different areas, but they all support each other and work as one. So that's why I'd like to call it a community rather than a cluster, because a cluster is just a random collection of entities. Something that we're working on at the moment is something called Strength in Places. A bid was put together back in 2019, and that was successful, and we are currently in the process of kicking off a range of activities which include collaborative research. And collaboration really extends through everything we do within the cluster, and I think you'll hear this from the speakers as we go through today. There are 4 discrete projects that are being undertaken under the Strength in Places banner, but these involve a matrix of all of the players within the South Wales region across a number of different activities. So with that, I'd like to go straight over to introduce our first speaker, and that's Andy Sellars from the Compund Semiconductor Applications Catapult. So Andy, over to you. Thank you.
Thank you, Chris. First slide, please, Georgia. Thank you, Chris, for the great introduction. So I'm Andy Sellars. I'm from the Compund Semiconductor Applications Catapult. So today I'm going to give you an overview of the Catapult and how we fit into this really vibrant culture, cluster ecosystem that Chris has described. So if you could advance the next slide, please, Georgia. Thank you. So what is the Catapult? Well, the Catapult is actually a non-profit research and technology organisation set up by UK government. There's actually 9 catapults distributed across the UK, as you can see on this map. We all focus on a different area of technology. So there's an advanced manufacturing catapult, there's a cell and gene therapy catapult, medicines discovery catapult, etc. And they're all located at the most appropriate position geographically, where there is already technology development in that area. And of course, our catapult, Compund Semiconductor Applications Catapult, is focused on helping UK industry exploit the advanced properties of compound semiconductors. And of course, we're located right in the heart of the cluster in South Wales. If you could go to the next slide, please, Georgia. So just briefly, what are compound semiconductors? Well, Chris gave an overview there of the advancements in silicon semiconductors. Well, actually, compound semiconductors are a new class of materials. They combine 2 elements to form a compound. And the reason why that's important is they actually outperform silicon semiconductors in 3 areas that we abbreviate to be power, speed, and light. So effectively, power is power efficiency. Compound semiconductors are more efficient than their silicon counterparts. They're very good for power electronics, for delivering power to electric vehicles, and to extend the range of electric vehicles. The second area where they're very good is in speed. Compound semiconductors operate faster than silicon semiconductors. That's very important for high-speed data communications. So the 3G and the 4G network was predominantly built with silicon and silicon germanium. As we advance to 5G and the next generation of 6G and satellite communications, they will be increasingly dependent on compound semiconductors for those high-speed data communications. And lastly, the area of light. Compound semiconductors very efficiently emit light and detect light. Now, arguably, silicon can detect light, but it can't emit light. Compound semiconductors are very, very good in this area, and they can be tuned to different wavelengths, different colors of light. And that provides a whole plethora of applications, from health monitoring to optical communications, and even into the quantum technologies. If we could advance to the next slide, please, Georgia. Thank you. So what are the key markets for the catapult? Where is our sort of key focus areas? Well, actually, we have 3 key markets. They are net zero, which is predominantly transport and industrial applications. We have future telecoms, which is predominantly 5G and satellite communications. And there's an element of synergy with the telecoms and defense applications, in fact. And thirdly, we have intelligent sensing, which is areas such as healthcare, diagnostics, and wearables. Now, internally within the Catapult, we are structured into 4 teams. We have a power electronics team. We have an RF and microwave team doing those high-speed applications. We have a photonics and sensing team doing the light emission and the light detection. And we have an advanced packaging team, which kind of brings together those other teams, really. I've got a bit more detail on a further slide. If we could advance to the next slide, please, Georgia. So net zero, what is our role in net zero? Well, predominantly, it's the big drive here is electric vehicles. As we move towards electric vehicles, that actually reduces emissions of carbon dioxide at the point of use. Electric vehicles are very clean to drive around. However, you still need to generate the electricity somewhere at some point in the network. And that requires a move towards renewable energy sources and very flexible energy grids. So as we move towards renewable energy sources, clearly solar sources and wind turbines they will generate a large amount of electrical energy when it is sunny or when it is windy. Therefore, it is necessary, because of the intermittent nature of those energy sources, it is necessary to bank that energy when it's windy or sunny, and then redeploy that energy when the consumer wants it, by charging up your electric vehicle. So these are the sort of 2 main areas where compound semiconductors are really prevalent, is driving electric vehicles, extending the range of electric vehicles, and creating flexible energy grids, allowing us to tap into renewable sources of energy as we go to a net zero economy. Next slide, please, Georgia. And I mentioned future telecom networks. So what do we mean by, where is the role for compound semiconductors in future telecom networks? Well, actually, here are some of the trends. So the 3G and the 4G network was predominantly built out using what are called macro cell base stations, which have got quite a wide area of coverage. However, as we move to higher data rates with 5G and 6G, we need other technologies to achieve those very high data rates and those very low latencies. And one complementary technology is called small cell base stations. And it turns out the UK is actually very good in this area. So small cell base stations will certainly start to complement the larger macro cell base stations that we have already deployed. As you put more data into a base station, and I've got an image here of a base station antenna, as you put more data into a base station, what it does, it creates a blockage somewhere else in the network. And that other part of the network is called backhaul. So actually, we need to increase the capacity of backhaul, and that is also done through compound semiconductors. Now, as we also roll out 5G and 6G services, we'll need to think about how we deploy those services in highly dense urban environments versus more sparse rural environments. And one potential solution to deployment in rural environments is via satellite communications. So, for example, we could create 5G corridors with CubeSats. All of these require compound semiconductors. Also, as we want to make our telecom network more resilient, we're going to be increasingly reliant on quantum cryptography, quantum encryption, another application of compound semiconductors. And lastly, the telecom network actually consumes about 3% of the global energy requirements at the moment, and it is increasing. So we need the efficiency of compound semiconductors to keep the energy consumption of the telecom network under control. If we could advance to the next slide, please, Georgia. So I've mentioned the Catapult's in the heart of the compound semiconductor cluster in South Wales, and you're very, very welcome to come and visit us. We have a 30,000 square feet centre, about 3,000 square metres, which is divided into 5 zones. We have a design studio where you can come and simulate and model your application, your new product. We have a class 10,000 clean room where we can do advanced packaging. We can take semiconductor die and package that die and miniaturize it to make advanced products. And we also have 3 proving testing laboratories. We have a power electronics laboratory, we have an RF and microwave laboratory, and we have a photonics and sensing laboratory. And we're very keen to work with companies, and we invite you in to come and see our facilities and to work with you to develop your next generation products. If we could go to the next slide, please, Georgia. So part of our role is to help develop these complex supply chains that Chris alluded to in his presentation. So this is a representation of a supply chain from a wafer, which is a pure crystal of semiconductors, to a die where we have etched some transistors into the semiconductor wafer. We singulate that to create a device, otherwise known as a chip, and we put the chip on a circuit board, and it becomes an application. So part of our role in the Catapult is to help bring these supply chains, these complex supply chains together to enable companies to develop the next generation products exploiting the advanced properties of compound semiconductors. And I've got an example. If we move to the next slide, I have a very good example of how we have in fact done that. So this is an example of a supply chain project that we have pulled together, and actually we're working on, we've initiated over £140 million worth of projects, but this is just one particular example that we're working on. And it is a supply chain creating a silicon carbide supply chain and a silicon carbide device, which becomes a power electronics module, and it goes into an inverter. And an inverter is a power electronics piece of kit that drives the motor in a McLaren electric sports car. So you can see this is a complete supply chain, right the way from the epi layer growth at the very beginning, silicon device fabrication, packaging module, to the inverter, into the electric vehicle. The entire supply chain created in the UK. And that is one of the strengths of the Catapult, as being very well connected across the UK. We can bring other companies into these supply chains. If we move into the next slide, please, Georgia. So we are very much an integral part of the ecosystem in South Wales that Chris has described in his presentation, and we'll be hearing from other parties as well as part of this cluster brief. So that uniquely, this cluster of activity includes pure research right out to product development and materials out to manufacturing. So it spans the entire ecosystem to develop advanced products within quite a small geographic space, and that makes it globally unique. And we welcome companies to come and work with us, to come and set up a design office and facility within our cluster. We can help you develop those very next generation products and help you to take them to market faster than your competitors. If we could advance to the next slide, please, Georgia. So I did mention telecoms, and it's been a bit of a recent focus for us for a number of reasons, actually. There's a lot of movement in this space. There's a lot of new technologies coming forward. There's some very big challenges to increase the data rates and to get the energy efficiency up, etc. This map here kind of represents the telecom network. It represents, from the left-hand side, you'll be familiar with your mobile phone, and your data goes into a base station which is the next step, the access fronthaul, and the signal then propagates through to backhaul, and it then goes into the core network. So the data transmits from left to right, and from top to bottom. The blue layer is the software layer, the orange layer is the systems layer, the yellow layer is the subsystems, and the bottom layer there is the components. And clearly you can see there's a supply chain here, and actually the UK has quite a good coverage for certain parts of this network. So we are very keenly working with companies in the supply chain to help develop the 5G and the 6G and improve the efficiency of the network. If we can move to the next slide, please, Georgia. And why this is particularly important at the moment is that there's quite a big focus on restructuring the telecoms industry. I'm more than happy for these slides to be made available afterwards, and actually these images are clickable. So if you would like to, you can go in and read the background or hear the videos. So there is, at the moment, there's a telecom security bill which has gone through Parliament, which is looking at disaggregating the network. And there's a telecom task force which reported earlier this year, and they're looking at opening up the market to new entrants. This provides a really great opportunity for UK companies to take a larger slice of the telecom network, and the Catapult is very, very keen to work with companies that might wish to do that. So please contact us if this is of interest. If we can go to the next slide, please, Georgia. Thank you. And I just got this slide and then one more afterwards. So part of our role is to understand what else is available within the UK. So we have mapped some of the other clusters of activity, and you know, to Chris's point, we are part of a very unique compound semiconductor cluster in South Wales, but that is also actually part of a slightly broader cluster of Western Gateway, and the Western Gateway has some really unique strengths as well as some artificial intelligence. South Wales Wales has some unique strengths in cyber. The Western Gateway has small cell base station capability. When you bring those together, you really do have a very unique proposition when it comes to telecoms. So this is a really vibrant South Wales cluster for the semiconductors, linking with a broader telecoms cluster just over the channel into Bristol, Bath, and Swindon. So it's a very exciting time, I think, to be part of this this emerging cluster that we're building. If we can go to the final slide, please, Georgia. And just as an indication of how we operate more globally, we have already signed an MOU. We believe it was the world's first virtual MOU with the Industrial Research Institute of Taiwan, ITRI. And we have also started to engage very deeply with the Department of Telecoms in India. And you might ask, why the Department of Telecoms in India? India is the world's largest democracy with 1.4 billion inhabitants. So it is a really great springboard country to work with as we sort of develop our aspirations to develop next generation telecom technologies. So very delighted to hear from anybody that would like to work with us. And my contact details are on the very final slide. Thank you, Georgia, for the opportunity to present. That's my final slide. Thank you.
Thank you very much, Andy. Lots of exciting stuff happening within South Wales that tends to be under the radar. I'm sure a lot of people are not aware of the high-tech activities that are happening here and have been for some time, but certainly due to accelerate with new and emerging technologies. So thanks very much for that, and look forward to speaking to you again later. If anyone has any questions, then please feel free to pop them in the comment section. It's now my pleasure to introduce Paul Meredith from Swansea University. We've made a number of references to Swansea and Cardiff universities, and there are some specific high-level investments that we'll hear from Paul and Peter from Swansea and Cardiff about. The first one being CISM, which is the Centre for Integrative Semiconductor Manufacturing. So as you can imagine, that's pretty specific to the cluster activities. So on that, I'll hand straight over to Paul Meredith from.
Thank you, Chris, and I hope everyone can hear me and see my slides. I'm Paul Meredith, as Chris says. I'm a professor from Swansea University. Swansea is a research-intensive university, and we represent the western edge of the cluster, as I'll show you in a second. And I want to speak to you today very briefly about our new Centre for Integrative Semiconductor Materials. I'll explain what that means and show you our aspirations about how we can support and intend to support the cluster going forward, particularly in feeding research and innovation services in at the low TRL levels and above. So, as I said, we are the western edge of the cluster. There are two universities within the cluster, Cardiff University and Swansea University, and Peter, my colleague from Cardiff, will talk to the Cardiff capabilities shortly. We are the western edge, as I say, of the cluster. We joined roughly 2 years ago into this now growing ecosystem that you've heard about of RTOs and important companies in the space. So at Swansea, we've had a fairly extensive and comprehensive semiconductor portfolio for a number of years now, probably for something near a decade. Our original focus in semiconductors was really around semiconductors and healthcare through our Centre for Nano Health that I'm showing here. And that's evolved, I guess, over the last 3 or 4 years into a more comprehensive program. Still very importantly, we focus on semiconductors in nanomedicine and healthcare, but we've also developed large portfolios, particularly in efficient power electronics, and that is specifically wide bandgap compound semiconductor power electronics, gallium nitride and silicon carbide. We have a large portfolio in clean energy systems, particularly focused around the development of next generation photovoltaic systems, and also the power electronics that one needs to run these clean energy systems efficiently, as Andy was talking about. And we have a new and emerging program in what you might call over-the-horizon semiconductors and applications which are sort of forefront at the moment, such as applied quantum technologies. And really, our provision into all of these spaces is around advanced semiconductor growth and processing, but also in packaging and the integration at the back end of these systems into full component level. We also have a speciality in advanced dielectrics. Of course, dielectrics are I guess, you know, a sometimes forgotten component in the semiconductor space, but dielectrics are very, very important elements of every semiconductor component, and some capabilities, quite advanced capabilities in simulation and modeling to go alongside the Catapult and what you'll hear from Cardiff as well. We have a very significant capability in advanced characterization as well, such as in advanced electron microscopy and surface analysis. So we currently run a clean fab with ISO 5, 6, and 7 areas, about 40 existing process tools, including wet and dry etch at 6-inch silicon and compound semi, a large range of deposition equipment, lithography and nano imprint, and some, as I say, some advanced characterization, which we can offer to the community. We have a total project investment of order 20 million with about 50 skilled researchers and 20 academics in the space. So it's now a significant activity for us. So in 2022, this will be augmented by what Chris has described, our new Centre for Integrative Semiconductor Materials. It will be built and is being built on our Bay campus, which is on the eastern portion of Swansea, very close to Swansea Bay. So quite a few of our cluster partners call it the new fab on the beach. It is an industry-focused facility which was co-designed by our partners in the cluster, designed specifically to provide underpinning research and innovation services to the companies in our cluster. A dramatically expanded cleanroom space, roughly 1,000 meters squared of ISO 5, 6, and 7. And a very flexible configuration and architecture with what's called a sub-fab. That is to say, the services feeding the fab from below, and the fab will sit on a floating first floor, very much like our industrial fab at Newport Wafer Fab that we'll hear about later. We will be capable of processing silicon, compound semiconductors such as 3, 5, and 2, 6. We have a new facility for processing wide gap oxides, and we can also deal with over the horizon material systems such as the 2Ds, organics, and perovskite tools. And we think this will be the first lab in Europe where we can process all of these different types of semiconductors together. The total space is about 4,500 meters squared, of course. 1,000 meters squared of clean room, but also the ancillary labs that people need to do these sorts of things, this type of research, wet labs and electronics and optoelectronics labs. And particularly something to highlight is that we will be taking delivery of and setting up a new metallic organic CVD reactor facility for 2,6 oxides and chalcogenized, which will be the only one in the UK. We can accommodate roughly 110 researchers in this space. And those researchers, you know, predominantly drawn from our academic partners and from the university, but also we have considerable facilities for incubators and also to provide space for small startup companies to get them off the ground. Alongside this, we'll have quite significant capabilities in advanced characterization and analytical as well. It fills, we believe, a UK capability gap in applied semiconductor science and technology, and is a complement to our sister fab at Cardiff, which Peter Smowton will tell you about in a second. The total investment is roughly 90 million into this new facility, and it's funded under the UKRI Research Partnership Investment Fund, which is a large infrastructure fund, whereby the UK government funds significant capital investments at UK universities. And our target completion for this is in 2022. And on the left-hand side, you can see some of our architectural mock-ups, what we hope this thing will look like. So I just want to spend a couple of seconds talking about this concept of integrative semiconductor materials. What is it and why are we doing it? Well, generally speaking, the semiconductor technology space has been split into what you might call silos of materials. First came silicon, as Chris talked about. Next came compound semiconductors, and next, I guess, is these new generation of materials and systems, the wide gap systems, the 2Ds, the organics and the perovskites. And generally speaking, these types of materials occupy different silos in technology space. What we propose to do is to kind of mix all these things up, provide an environment where they can all be processed, and we can make devices from all these materials and kind of shake it all up to see what comes out, to develop new technology interventions. So, for example, some of the technology and materials we're interested in, gallium nitride and silicon carbide power electronics and optoelectronics, wide gap systems. We will have a program in the new wide gap oxides, gallium oxide, for example, for power electronics. As I've mentioned before, the organics and perovskites, which are over the horizon type of materials, and advanced and high K dielectrics, key to all of these technologies. Chip level integration, and then utilizing the next generation systems on silicon and compound. And the services, well, fundamentally TRL 1 to 6 services supporting the cluster partners and the broader partners now coming into the region. Bespoke blue sky and R&TD services, but also offering up all of the facilities that we have as a university in analysis and characterization. Looking to assist with prototyping from TRL 1 up to 6, as I said. Also looking to provide incubation services. And something you'll hear about this afternoon, a key part of the university's provision, our provision and the Cardiff's provision, is providing professional graduate level training into this ecosystem to fuel the pipeline of talent that we need to grow the cluster. And we'll talk about, we'll hear about that this afternoon in skills and other engagement activities. Okay, so our partners within this, we have the CSconnected cluster core partners, but also many other partners from outside the region, and inward investment partners such as Rockery and MicroLink devices. So you can really see how this is a comprehensive and coordinated approach within the cluster. And also new partnerships coming in as we seek to furnish the fab, buy new tool sets. On the right-hand side, you can see a bunch of new partners that are coming in that provide tools and services. And of course, our core university partners, Cambridge, University of Warwick, Leeds, Imperial College London, and a growing number, as well as our sister university in Cardiff. So this is currently what it looks like. This is as of early June. We have made progress on the build, even despite of COVID. And as I say, we're on track to deliver this facility in mid-2022. So in 2022 as well, we will have an upgraded tool set capability that will be offered to the cluster. Roughly 50 tools. I've gone through some of the facilities a little bit earlier, but in all of the key areas of semiconductor device and wafer processing, and indeed deposition with our new MOCVD suite. So deposition, lithography and etch, back end, and analysis and characterization. And I just want to highlight one particular issue, and that is the capability we'll have in the development of dry etch processing. We probably will have one of the most comprehensive dry etch processing capabilities anywhere in the United Kingdom. And that will be a key focus for quite a few of the projects that we're involved in going forward. So just as a couple of examples at the end in the last few slides of some of the projects that we're involved in, which are very important for the cluster. For example, we were recently awarded under the ISCF Wave 3 priority, Driving the Electric Revolution Industrialization Centres, funding to establish a wide bandgap power electronics industrial pilot line, which was about £4.8 million worth of funding. And this is to set up the UK's first wafer to component level silicon carbide industrial pilot line. And that equipment will be shared across Newport Wafer Fab, our cluster partner, and across Swansea. And the tools that will be installed as part of that pilot line are all industrial tools for wafer level component processing, etch and deposition, back end and package, test and measure, and component design and modeling. And as I say, these tools will be deployed across Swansea, our new fab, and Newport Wafer Fab. And the timeline for that would see us hoping to have this pilot line ready by mid-2022 to accept projects and start development work for the cluster and the broader power electronics UK community. Another project that you've heard about already that we play an integral role in is the Strength in Places Fund Wave 1 CSconnected project, and particularly providing underpinning research and innovation services to several of the collaborative research and development projects. There are 4 of these, which I'm sure you'll hear a little bit more about. For example, in the first of those projects, we're involved in helping produce the distributed feedback indium phosphide laser processes and passive waveguides on an 8-inch platform using something called nano-implant lithography, which is an emerging technique in semiconductor lithography. In CRD2, in the Collaborative Research Project 2, we're working with MicroLink devices in helping them transfer their process from the United States into South Wales for their innovative photovoltaic cell technology, and you'll hear a little bit about that later on from MicroLink. And in CRD 3 and 4, we're actually providing back-end services such as die etch, processing, contact, dielectric deposition, and encapsulants into a range of products, including in the power electronics space. So with that, I'll finish. If you have any questions, of course, they can be directed to us in the Q&A, and very happy to talk to anybody offline about the work that we've got going on here at Swansea. Thank you very much.
Thank you, Paul. That's great, and I think it's showing how the whole of the story and the supply chain really comes together. We'll be talking or hearing from some of the companies in the cluster a little later, but the next presentation is from Peter Smowton at Cardiff University, who will be talking about another dedicated facility called the Institute for Compound Semiconductors. And I should add that these are very complementary. So we have the CISM and the Institute, the ICS, which are undertaking complementary technologies. You heard a lot about wideband gap materials for power applications from Paul, along with Photonics, which ties in nicely with yesterday's event and the launch of Photonics Connected. And Peter will talk about the activities that take place at Cardiff. I would just say one question that came in, and I think this will become clearer as you hear today's presentations, was about how the compound semiconductor cluster engages with Internet of Things and smart cities and so on. And I think you'll hear a bit more about that when we hear from Peter about connectivity and so on. But at the heart of all of these major initiatives like smart cities and so on, there will be compound semiconductors. But as I said right at the beginning, the supply chain is not obvious. What we'd like to do is to bring back to the UK some of the manufacturing opportunities that use compound semiconductors, rather than shipping it around the world 2 or 3 times before it comes back and gets incorporated. So thank you, Peter.
Okay, thank you, Chris. Hopefully you can see my slides now. As well as talk about ICS, I'm also going to talk about the CSconnected Strength in Places activity, which incorporates all the partners from the cluster. So I'll get on and do that, but very much from a Cardiff perspective. And I think what that will allow me to do is also just give you a little detail about what we're actually doing, as well as the broader picture. So Cardiff University compound semiconductor activity is subdivided into 3 areas. Facility, that's infrastructure and expertise. That's the Institute for Compound Semiconductors, which has already been mentioned. Research activities, and that includes academic groups and large grant activities, such as the Compound Semiconductor Hub. And then training activities, which includes things like our Centre for Doctoral Training in Compound Semiconductor Manufacturing. And then we've got this large Strength in Places activity, which Paul mentioned already, with various collaborative research activities, which is subdivided into 4 areas. And so really that connects that research activity within the rest of Cardiff University. It connects it to our industrial partners, but it also allows us to feed a capability back into our facility, because that's infrastructure and expertise. And so we're generating within the region a long-lasting expertise and capability through this program. And then another part of this Strength in Places activity is training, is skills. And actually, as Paul said, that will be discussed this afternoon. So I'll leave that for now and focus on the R&D programs. So what are in those 4 areas? Well, as has been mentioned, comms, communications and sensing is a very important area. And so the first of these large packages of research is focused on that area. 5G activities in this package, essentially for the backbone, that optical communications backbone for 5G, but also things such as sensing, LiDAR for vehicles, or even LiDAR for facial recognition in your smartphone. The second large activity is around scaling up semiconductor activity that is already done in industry. So compound semiconductors are following a path that has been described by Chris for silicon, and the scale up there of the number of transistors was made possible partly by the simple scale up in the size of the pieces of semiconductor that were worked on. And so what we're doing in this second research package is scaling up the compound semiconductor manufacturing process in the same way. In the third area, and I will mention in detail activities that Cardiff's doing in those first 2 areas. I won't in the second 2 areas, but I'll just quickly mention them now. The third area is all about scaling up the fabrication tools and the capability there, the manufacturing of those tools in the region and of all the components for those tools in the region. And we're helping there, very much facilitating new processes on some of those manufacturing tools, such as, for example, creating the mirrors for semiconductor lasers by plasma etching them rather than simply cleaving them. Part 4 is again supporting 5G, but also that autonomous electric vehicles and electric vehicles per se through the electronic components. And that's again a very big project, but our part in that project is actually looking at some of the heat sinking of these components and introducing novel ideas like the growth of diamond on compound semiconductors to create a diamond heat sink, or the wafer bonding of compound semiconductors to diamond being a very, very efficient heat sink. But I won't talk more about those latter 2, but I will about the first. But before I do that, let me just go and talk a little bit about, again, in this first box at the top, the facility, the infrastructure and expertise of the Institute for Compound Semiconductors. So what is ICS? What is the Institute for Compound Semiconductors? It's actually a fabrication facility. That's the 3D structuring of these semiconductor materials. We don't do what is termed the epitaxial growth, although we connect to it via academics groups in Cardiff and elsewhere and in industry partners. We don't do the device characterization, the devices that are produced by this process, although again, we connect to it via academic groups in Cardiff, and we can arrange services complete the way through. But we don't do that within ICS itself, and I'll explain why now. As a facility, the ICS doesn't do research itself, although that's done elsewhere in Cardiff University and elsewhere. And the reason we don't do that is we don't want to compete with our customers. And our customers are from all over the UK, from both academics elsewhere in other universities and from industry, because ICS is a pay-to-use open access facility. And hence you can see the value of taking this very large development activity through Strength in Places and putting that expertise and infrastructure back into ICS so it's available for all to use in the future. ICS will be delivered in 2 phases. The first has occurred, and that's an upgrade to our what we call our Queen's Clean Room, and that's now a 6-inch capability for wafer manufacturing. Phase 2 will be a new 1,500 square meter clean room, which will allow us to process 8-inch or 200 millimeter wafers as well, and that's all to do with this scale up that I talked about earlier. And what technology readiness level do we address? Well, obviously for researchers, we address low technology readiness levels, but we also allow small scale production. And again, that's why we don't want to compete with our customers who will be outsourcing those things to us. So where do we fit in this manufacturing supply chain that was described by Andy earlier? And these are examples of where ICS could fit. So there's a process from this epitaxial wafer growth all the way through to the application. The epitaxial wafer growth is essentially the atom by atom deposition of these compound semiconductors to create some functionality on wafer. But until you then three-dimensionally structure those semiconductors, you don't get that full functionality. And that's the role that the Institute of Compound Semiconductors plays, turning those wafers into devices. They are then handed on to other partners, such as the Compound Semiconductor Applications Catapult that Andy described, to look at packaging, for example, evaluation modules and subsystems before completing that supply chain. So in a research and development environment, we have a supply chain within South Wales. That's the top line. But that can also be small-scale manufacturing, as I've described. So if you're a startup organization, you can do your R&D in South Wales, you can transfer that to small-scale manufacturing. And then, of course, the normal problem is, how do I then scale up beyond that? Well, the cluster in South Wales has also assembled large-scale manufacturers of these semiconductor activities. So we've got IQE as a semiconductor wafer manufacturer, Newport Wafer Fab is the equivalent of the Institute for Compound Semiconductors, but at huge scale, and then Microchip for the packaging activity. So I hope you agree that's a really good ecosystem for people to start their companies, their outsourcing companies within South Wales. Let me take you back to some of the developments we're doing under this Strength in Places activity. And this is the first of these large chunks of research, the next generation optical communications and sensing. And Cardiff's role within this activity is certainly doing design of those epitaxial layers. So what layers do I put down? What materials should they be? What thicknesses should they be to create a certain function? And then we also do the fabrication of those alongside with our partners to create optical amplifiers and semiconductor lasers. And that's a picture of a semiconductor laser on the right. However, in the future, there may be alternative technologies that go beyond these initial technologies. And so we're also developing those within the project. So we're one step ahead. And so within Cardiff, we're actually doing some of the epitaxial growth as well as development and creating what are called quantum dots. And the reason for these quantum dot materials is they provide a really broad gain spectrum, which gives you options to have tunable lasers that operate over a range of wavelengths, or optical amplifiers that operate over a very, very broad range. They have reduced temperature dependence, and they reduce something called the pattern effect, which is actually how well an amplifier works or how reproducibly it works as you change the series of inputs that come to it. So, for example, if you've asked it to amplify a lot of ones in your system, bright amounts of laser light, does it work as well as when you've asked it historically to amplify a series of zeros or a smaller number of ones? And quantum dots allow you to do that in a much more reproducible way. So what does that involve? Well, it involves taking these big MOCVD reactors, changing the growth conditions, changing some of the growth parameters to try and create on the surface, as shown here at least, of the semiconductor, a series of inclusions which are of the dimension of the electron wavelength. And that's to change the properties of the electrons within that material. And I won't go into detail, but there's a whole load of variables you have there, and you have to experiment and produce out as uniform as you can a series of these very small inclusions, and to do that in multiple layers, and then to put it within some of these optical structures, either amplifiers or lasers, which requires some further optimization. So that's the research going on there in that particular area. Let me now go on to the second area, this scale up of this manufacturing capability. And I've chosen one of the particular structures that we're looking to scale up, the so-called VCSEL, or vertical cavity surface emitting laser. This is an electrically pumped device where we don't have quantum dots in these structures yet. We have multiple quantum wells. We create feedback for a laser using what's called a distributed Bragg reflector. That's lots of very thin layers with precise thickness to reflect light so that it constructively interferes and creates the conditions for lasing action. Within the those layers are put in within the epitaxial growth, but then the 3D structuring has to make the device have the right diameter. It has to put metal contacts on, and through oxidation of one of those epitaxial layers or more, it has to create current confinement to put the to make the device the right size and to give it the right number of lasing wavelengths. And all of these things have to be done when you scale up this manufacturing capability. They have to be done over very large areas. So that's what we're trying to achieve. So within the epitaxial growth itself, there are lots of things you have to worry about in order to create something that is the same over the whole wafer. And I've listed some of those on this slide. Now, we, as I said, aren't doing the epitaxial growth for this particular project. That's been done by IQE, one of the commercial partners that you will hear about this afternoon. But they have to monitor all these things, and we have to see what the effect they have, if they do vary, on the device performance. We do.
Sorry, I didn't quite catch that. Can you please?
We have to do the fabrication of these structures, the 3D structuring, and you can see here some of the etched structures.
Sorry, I can't do that.
Some of the etched structures, and then the oxidation of those layers. And what's interesting here is that we're actually using a steam oxidation process. So this device, which is at the heart of the facial recognition system in a modern smartphone, this very newest technology, is actually steam powered, and I always find that quite amusing. The pictures on the right actually show the detailed automated characterization we have to do on all of the devices on these wafers to understand how well they're working across the full 150 millimeter or 6-inch wafer, which is shown on the far right on the test platform. And before I'll go on and show you some of the results across that. So what you can do is you can automatically look across that wafer and perform some heat maps for how well various parameters are working. In this case, this is a heat map of the lasing wavelengths we're getting from lasers from across this 6-inch wafer. You can do more complex heat maps, and here is actually a heat map for the IV characteristics of those lasers, those VCSEL wafers, but this time in a much more dense pattern for full-scale manufacturing. And what we're looking at there is something like 150,000 VCSELs on that 6-inch wafer. And here you can see what goes from a single VCSEL device with an RF pad to drive it at high frequency. It's scaled up from a single device into squares of 100 devices. Those squares are put into 1-inch tiles. Those tiles go on a 6-inch wafer. So in this case, we've got about 18,000 devices on a wafer. This is because it's a test structure that we've employed to look at the uniformity across 6-inch wafers. And there below in the picture on the bottom right, you can see 5 6-inch wafers that we process sequentially to understand the distribution of performance across multiple wafers and across each of those wafers. Okay, let me leave you, as I've run out of time, with a picture of our new facility. This is this £150 million building, which is going to house the Institute for Compound Semiconductors and also our partner institute in Cardiff, the Cardiff Catalysis Institute. As I said, it's essentially a 1,500 metre square clean room at the front. It opens in June 2022, and it will allow us to go to even larger wafer sizes and continue this process. Okay, I'll stop there, Chris, because I've run out of time.
Thanks. Thanks very much, Peter. Great overview of both ICS and also of some of the exciting work we're undertaking under Strength in Places, and also great demonstration of technology in action with Siri kicking in.
Yes.
We're going to take a very short break now, and when we come back, we'll hear from some of the industry partners, and then there'll be a general Q&A at the end of the morning session at around about 12:15. So thanks very much for that, Andy, Paul, and Peter. And I guess taking a hint from the Siri activity, I should say, Alexa, turn the kettle on. See you back at 11:15. Well, welcome back after the very short coffee break. Hope you managed to get some sustenance and ready and primed for the next session. We heard in the first session from the CSA Catapult and from the initiatives undertaken by Cardiff and Swansea universities. And as we enter the next session, we'll hear from some of the industry partners about what their role is within the cluster and some of the activities that they're currently undertaking in what is seen as the world's first compound semiconductor activity a cluster, and also really is the center stage, or puts Wales at center stage in this particular technology area. So to start with, I'm introducing Richard Barnett. Richard is with SPTS. SPTS is an equipment manufacturer based in Newport and has a long history within the region, and works very closely with quite a large supply chain, much of which is within the South Wales region. So if I can introduce you, Richard.
Hi. Good morning, everybody. Thank you. Thank you, Chris.
Thank you.
So just waiting for the slides. Perfect. Thank you, Georgia. Let me... Okay. So SPTS is, as Chris just mentioned, a manufacturer of etch and deposition equipment. And rather than just the hardware, we also develop the process solutions that go along with it. And we supply the wide semiconductor manufacturing industry. Chris also alluded to our long history. Some of you with longer memories might recall names such as Electrotech, Tricon, STS, Avisa, but now we're all SPTS technologies, and part of one of the larger semiconductor companies in KLA. That's been the case for the last couple of years. Now, we operate where you would expect us to operate in terms of supporting the customer base right across North America, Europe, and across Asia. We're headquartered. SPTS is headquartered in the UK, as Chris mentioned, again in Newport in South Wales, where we do the vast majority of our manufacturing. And we also have a small manufacturing site in the US for our release etch products. In Newport, we manufacture our etch, PVD, and CVD equipment, the Omega, the Sigma, and the Delta. And from there, we also have local teams in and around the customers supporting directly all of our equipment in the field. Our headquarters, I mentioned in Newport. We have all of our design and development engineering there, all of the management and ancillary tasks, as well as our manufacturing. We've got just over 100,000 square foot of space. We've got 28 module assembly cells. We can test 32 modules at a go, and we have a 6S controlled class 1000 clean room environment. The neat thing about the way that the workforce is put together is that everyone can pretty much crossover in terms of a manufacturing and testing portfolio, so we can expand or contract depending on market conditions. And we have a very strong lean manufacturing continuous improvement culture. So we're always looking for the best and most efficient methods for manufacturing the equipment. And as part of that, the design of the equipment, the design of the processes as well, takes into account ease of manufacture, ease of servicing as well. So we always have one eye on where the equipment will end up. A couple of images of the manufacturing facility in Newport. So you can see we've got a variety of shadow boards. We've got dedicated regions for making the equipment, all under the Class 1000 cleanroom control. Test areas with laptop control rather than any paperwork. We use a system called Shop Floor Online. So everything is recorded, everything is traceable, and we have a great history build of the equipment from first parts right through to its service in the field. As a business, it's no surprise that the majority of our equipment gets exported. Most of that goes to Asia, and then Europe and North America vie for second and third places. In terms of end market, we supply across the widest range of the semiconductor industry, apart from the traditional front end where you would find memory and logic devices. We've got a very strong presence in compound semi, and why becoming part of the cluster was really an easy decision for us because of our presence in that manufacturing area. As you can see, that RF, power, and photonics, listed as LED here, form quite a significant part of our end revenues. In terms of where the revenue comes from by technology, the etch and deposition technologies from Newport form the sort of the major percentage of that revenue, with our release etch, our applications and spares and service filling the rest of it. And as you can see, the vast majority of the manufacturing is done in the UK, and that goes hand in hand where the revenue comes from. So the equipment that we manufacture goes across the whole semiconductor industry, from advanced packaging, so where memory and logic devices need to be put together in new novel ways to save space or to increase performance. It's a way of continuing the progression of transistor growth without the difficulties associated with shrinkage. MEMS devices, I won't mention her name because I've got one near me, but the types of home speakers, the gyroscopes, accelerometers that you find in your phones for changing the screen orientation, we've got a significant install base for the applications for creating those MEMS structures. And then we get to some of the areas where compound becomes much more prevalent. So power semiconductors, Andy, Paul, and Peter all mentioned these, and Chris did in his opening introduction as well. Electric vehicles, hybrids, higher efficiency white goods, all of those devices rely on power semiconductor chips manufactured with compound devices, and the SPTS process and equipment is used to create those chips. And then every device that connects to the internet does so through a compound semi created chip. So whether that be the RF filters to filter out the frequency or the band needed for connecting to a certain certain provider, or indeed the power amplifiers to boost the signal in order for it to be used. So I suppose everyone is carrying some compound semi around with them, even if they don't know it. Photonics is an area of considerable growth at the moment, with lots of the autonomous vehicle sensing relying on optical lasers rather than things like radar. So the photonics in creating the lasers, the VCSELs that Peter spoke about just before the break, even simple domestic and industrial LED lighting is manufactured on a chip, on a wafer, using our equipment and our processes, and you're beginning to see these sorts of things appear everywhere: head-up displays, augmented reality glasses, and so on. And then we've got a small amount of equipment that goes to the mainstream devices for front-end processing. But the vast majority of our process and hardware know-how are in the advanced packaging, MEMS, power, RF, and photonics areas. So looking at what we have for compound semi in total, this matrix here basically covers all of the products from SPTS. You can see down the left, we've got the etch, the deposition, the CVD, PVD, our release etch, molecular vapor deposition, and our the thermal products that we represent. And then across the top are the 5 key markets: MEMS, advanced packaging, power, RF, and photonics. And where we've highlighted in yellow, there's a direct link to a compound application. So in MEMS, for harsh environments, silicon carbide shows its place there. For power devices, it's GaN on silicon or GaN on silicon carbide. Basically, those are the power devices that we spoke about, and then silicon carbide and silicon trenches for some of the isolation activities. Then in RF, I spoke about the devices used for connecting to the internet, the filters, the power amplifiers. So that's, for us, that's gallium arsenide, silicon carbide as well. And then photonics is where the list of materials expands. So you go from gallium arsenide, indium phosphide, gallium phosphide, lithium niobate, as well as many other exotic materials. So in the etch world that I represent, we've got quite a big finger in those pies there. And then our colleagues in the deposition applications, whilst they may not be working directly with those materials, they're working on the processes and hardware that go along the associated steps within the process flow. So for CVD, for example, it's low damage silicon nitride for the gallium nitride applications. Low damage deposition is just as important as low damage etch. You don't want any of the physical component of the process to create any issues on the films already there. And then for our PVD colleagues who are dealing mostly with the metals, there are some wide bandgap materials that they can deposit on for interconnects, for barrier, liner barrier deposition as well, if it comes to via connections, 3D connections as well. So I'll speak a little bit more about how we're involved with the cluster. You'll see this a number of times or something similar across all of the talks today. You've got the IQE and the Compound Semi Center looking after the substrates, and then you've got the university guys looking after sort of devices, manufacturing technologies, design of performance and functionality. And then we've got Newport Wafer Fab and Microchip, who you'll hear from later, actually manufacturing the devices and packaging. For SPTS, we sort of sit right in the middle of all of that, because we develop the processes or some of the processes and some of the hardware needed to create the structures, to form the interconnects, to take that base material and form in use by the foundries and the packaging guys to form the actual devices. And of course, where we sit is across all of the activities of the cluster, whether it's the university fabs at CISM, the foundries at Newport Wafer Fab, or potentially with things like the use of plasma for singulation of devices at the back end in the packaging step as well. So our involvement, firstly, because of our geographic location, is it's a no-brainer really for us to be involved in this. Plus, of course, our market presence in compound semi. But rather than it just being a coincidental benefit, we have a very strong partnership and a well-aligned scope and vision with all of the partners in the cluster. All of the key drivers that are building the production ramp, not just in the UK, but across the rest of the industry, in automotive, whether that's autonomous vehicles or electric vehicles, the race to reduce carbon emissions, the recent coronavirus situation that's accelerated the use of certain medical devices, the final sort of beginnings of the 5G infrastructure coming into place, the early development of 6G, even if we're only just getting our heads around 5G, Internet of Things, all those things that are driving our markets, our industries, will be beneficial to SPTS from a commercial point of view. But having the expertise and knowledge around us from the cluster will certainly help us to be able to take advantage of that. The inward investment has been considerable, and Chris covered that earlier on as well. The community aspect is vital, really. Whereas we would be wanting to get involved in certain funded project work. As a standalone organization, we would probably find it hard to come up with the breadth and detail of the applications that we've been able to do so as part of the CSconnected. Strength in Places is just one of those, and it was a significant application for that program, really, which showed the strength of the cluster in all manner. Obviously, we've got the universities and we've got the foundries nearby. So that talent pipeline, I think Paul mentioned that. Getting students through the right sort of courses with input from not just the academic side in terms of the theory, but also having some external opportunities so that when the graduates come out, they are well versed in all of the aspects of the technology, so that they become much more useful much more earlier in not just SPTS, but in some of the other local organizations as well. Then from a practicality point of view, whilst we can do so much development in-house on processes and the hardware to produce the outcomes that our customers will need, understanding how our parts actually interact with the device performance, so prototyping and such like, and testing, all of this is going to be vital for us going forward, particularly with a view to helping establish for certain applications a UK-based supply chain. And of course, we benefit from having opportunities to place our equipment around us in our locality, at CISM, at Cardiff, Newport Wafer Fab, and so on. Then something that's not so obvious from the outside, but we're able to take advantage of the cluster opportunities to help establish a better manufacturing and supply chain organization. Obviously, we're expecting this to all generate new business for us, not just from a UK perspective, but worldwide. So we'll need to be able to build more equipment, and we'll want to do that efficiently. We'll want to do it environmentally friendly. We'll also want to do it with one eye on economics as well. But one thing about SPTS is that we try and source as much as possible from within a local supply chain. Not only is that good for the local economy, but it's also good for us as a business because we have very close ties with those suppliers. And part of the work from the Strength in Places activity is to help bring the standard of the local supply chain, metrology, inspection, testing, or whatever, up to sort of another standard as we grow, as SPTS grows with our ramping. We'll be looking to help the local supply chain come along with us. And then you put all of that into one sort of big block, and then we're looking at where the external partners want the devices, want their products to go longer term. And so that has a net influence on the functionality, and then that has an influence on how the devices are put together. And then that's where we get involved in working out the process detail necessary to provide those longer term application developments. We're involved in a lot of funded projects. I mentioned that just a second ago, and how difficult it would be for us to do on our own. But you can see down that list of partners in one of the columns that we're involved with all of the Compund semi-cluster partners in a variety of programs, not just the CSconnected high level activity. And so it gives us opportunities not just to concentrate and collaborate on Compund activities, but as you can see, there are things like biomems on that list as well, which may involve Compund, but generally doesn't. So we're able to sort of take advantage of those links and relationships in that way. I've already mentioned strength in places. So we fit in the Collaborative Research and Development Project 3.3, which is tasked with looking at novel and efficient fabrication of equipment for compound semiconductor applications. And it's about scaling up, as I mentioned, and it's about making sure that the quality in the supply chain is there, as well as in our manufacturing processes. And we do that. I've already mentioned the increase in capacity and the supply chain development. That's in the hardware and manufacturing side. And then we've got the process developments as well. So sort of in the near term, we've got the GaN on silicon, indium phosphide, and the VCSELs. All of those will have real world activities, real world applications right now. And then looking a bit further out, moving of silicon carbide up to a larger wafer diameter, which makes it cheaper to make. Looking at different materials, looking at new process modules. Our current technology works, which is great, but it needs to work for the next gen or the next generation of equipment, materials coming through. And then we've got the things like use of plasma for singulation, GaN on diamond, and so on. And we'll be pulling on all of the cluster partners to understand where we can support that. A couple of projects very quickly on what we're working on. So GaNT is looking at a vertical gallium nitride structure. There's numerous partners involved in this one. Swansea is one of the key ones, I think, and Cardiff. And so we're using our Synapse process module, our molecular vapor deposition, our PVD equipment and processes to help produce this structure, which will be able to help with the acceleration and the explosion that's coming along with EVs and hybrids and working towards net zero. And then Socrates, which is along a similar line, is focusing on silicon carbide transistors. So this is part of the Driving the Electric Revolution. And we're looking primarily at, as you can see from the images down here, the shapes of the silicon carbide trenches and how they really affect the functionality and then the performance of the end chips. I've probably taken a little bit longer than I ought to. So I'll just summarize here by saying that we're a key partner in the CS cluster. We're sort of working on the process and hardware for the device manufacturing, and we're working with all of the players in the cluster to achieve a great outcome for all of us, not just on a local concern, but on a wider worldwide scale as well. So thanks very much.
Thank you, Richard. That's great, and helps to put everything into context in terms of both the manufacturing process and also in the equipment and how closely integrated the two are. And as I think has been stressed throughout this morning's session, if you carry a handset, use a medical device, use a range of technologies, if it's not made in Wales, or the starting point is not made in Wales, there's a good chance it's being processed on equipment that's made in Wales.
Absolutely.
So we play a really key role in this little corner of the planet in terms of new and emerging technologies. And as we move to electric vehicles, that's going to be even more the case. So thanks very much for that, Richard. Excellent.
Thank you, Chris.
Thank you. And our next speaker is from CSC. Ali Anjomshoaa is with CSC, the Compound Semiconductor Centre, and Ali will talk about the role of the CSC, which actually fits neatly between the universities and the high volume manufacturing. And as I mentioned in the introduction, is the joint venture between Cardiff University and IQE. Apologies if I've taken away something you were going to say in the first couple of slides, Ali, but I'll hand over to you now. Thank you.
Thank you very much, Chris. Thank you. And good morning, everybody. And let me just start my timer so I can try and keep to time as best I can. So as Chris said, I'm Ali Anjomshoaa. I'm a program manager at the Compound Semiconductor Centre, and my focus is on photonics. So the Compound Semiconductor Centre came into being about 5-6 years ago, 2015. If you look at our logo, it looks like a clasping of hands. So it's IQ and Cardiff University working together. And what we're here to do is to translate R&D into commercial propositions. So Cardiff does a lot of research, great pedigree, many years of research in compound semiconductor design and devices. And IQE is one of the world's leading, if not the world's leading, compound semiconductor manufacturing of wafers, so wafer materials. When we talk about translation and commercialization, so although we are focused on the materials and the wafer side of things, as a team within the CSC, we really handhold with our customers to take them all the way from the materials and what they need in terms of the specifications and requirements right the way to the end design. And this is why working within CSconnected and the cluster in South Wales adds so much value to what we do, because we can work with everyone in the cluster to go from design, modeling, right the way through to materials, testing and packaging of devices in terms of prototypes and commercialization. So it's really important to be part of this cluster. So I said we were born in 2015, 50-50 joint venture between Cardiff and IQE. We're based at IQE's St. Mellon facility. And in fact, we have 15 MOCVD reactors there. You can see one there at the bottom in the center, an Extron reactor. And these reactors are used to epitaxially grow crystal layers on a substrate. You can see on the top right there. So you grow hundreds of films potentially of substrate onto the substrate, atomically engineered. The bottom right shows a sort of part of the periodic table. Silicon is a group 5 material, and either side 3,5 and 2,6 materials form compound semiconductors. Okay, and we're focused on gallium arsenide, indium phosphide, GaN for RF and power. Primarily, we work in collaborative R&D projects and programs. We work with customers as well, so commercially, privately, as well as grant funded. And today, I believe, if I haven't got that wrong, we've got project win values of £80 million thereabouts. So, moving straight on to strength in places and CSconnected then, you've seen this idea that we've got 4 streams of project activity within strength in places. Okay, there's an entire program is about £40 million worth, about 27 million of funding from public sector. And so where do we fit in? I'm just going to talk straight into where the Compound Semiconductor Centre fits into the 4 programs. So we are looking at sensors and communications optically, so that's photonics. I'm mainly involved in that first group on the left there, that boxed next generation optical communications and sensing. But we're also involved in the tool development that you've just heard from Richard at SPTS talking about, developing these new tools for the processing and fabrication of devices. So we provide novel material structures and substrates into that, and we provide, if you like, an output from them to tell us what is right, what is wrong, how we can optimize, and so on and so forth. But we essentially help that tool development, next generation tool set development work. And the box on the right there, advanced processors for 5G. You've heard of 5G. We're of course already looking at next generations and next generations of wireless, radio frequency technologies, and EAVs are sort of electric and autonomous vehicles. You've heard from Richard and others already. A lot of power electronics use compound semiconductors for high current, high voltage switching and management of the electronics there. So the power electronics use a lot of compound semiconductors. So I'll talk about each of these in a slide. So that number one, CRD1 I talked about, which is optical comms and communications and sensing. I'm going to talk very high level. You've heard a lot of details about these devices, the materials and so on and so forth, and the etching and processes and fabrication. But I'm going to stick at the high level and tell you what they're used for. So we're developing these photonic materials and devices. The first picture there shows you a very busy, if you like, data center type scenario where you've got lots of racks of machines, and these racks and computer nodes need to talk to each other at very high speeds. And a lot of the communications are done optically now, so they need lasers and photonic detectors so that the messages passed between these machines and the outside world can be done extremely rapidly, very high bandwidth. So the photonics aspect is all compound semiconductors there, whether it's the source, the lasers, or the detectors that detect the light signals coming through. Okay, and we call these light sources, we call these active devices. They generate light, they amplify light, and the three main different types of devices we're concerned with on the project are edge emitting lasers. So these are lasers that put light out through the edge of the device, the chip. Vertical ones, which put light out through the top or indeed the bottom, they can do, so basically they're putting light out perpendicular to the surface of the device, the wafer, and semiconductor optical amplifiers, which as it says, they amplify the light. Okay, that goes through them, and that's for signal propagation and making sure we can go further and have more signal to work with. And within the Strength in Places project on that first CRD1, what we're doing is we're integrating these active and passive devices. So passive devices are things like light guides that guide the light around into very complex photonic integrated circuits, and silicon photonics is generally used to talk about that. Once we do that, we can have very complicated photonic integrated circuits to go into things like smartwatches and mobile phones and other devices that can do sensing. Okay. So in terms of the applications there, I've already talked about high-speed optical communications and data centers and so on. And sensing also, we can do sensing for environmental, for process industries, for healthcare, and so on and so forth. It's not just in consumer devices, but it's wider aspects as well. Let me just check actually that my slides are indeed changing. Yes, they are. Excellent. So the next one is this CRD3, so the third collaborative research work that we're doing with SPTS that Rich has just been talking about. You've heard lots about that already, so I won't go into too much detail. Essentially, this is a next generation of tool sets, looking at next generations of materials for next generations of devices. So it's really about getting finer features, facets into these three-dimensional atomic layer structured devices. Okay, and the three aspects there I've already talked about we're involved in, but VCSELs, indium phosphide photonics, which is the area I'm involved in for edge emitters, edge emitting lasers, and also gallium nitride on silicon for power electronics such as battery management and so on for electric vehicles, and also RF, the radio frequency of high-speed wireless telecommunications. Okay, so I won't go any further into that, but we essentially provide materials for that work. Moving on to the CRD4, so Collaborative and Research Development Project. This is the fourth stream of CSconnected's Strength in Places work. A lot of 5G, but of course we're looking at the next generation systems as well, higher frequency, wireless communications, radio frequency. You can see some of the pictures I've put up. You've got a mast there, you've got a radar on top of a helicopter, you've got satellite communications. All of these use the high frequency and high power systems that use the compound semiconductor devices we provide. You'll hear a lot of talk, and you have heard a lot of talk about different sizes. You see a wafer there. I'm estimating that is indeed a 4-inch wafer, so that's 4 or 6 inch. I can't quite tell with the scale of the hand, but nevertheless, so 150 millimeter wafer is a 6-inch wafer. And of course, what you want to do is you want to move to bigger wafer platforms. So you've got more devices on a single wafer, which has gone through a single growth run. So you hear a lot about moving on the higher wafer sizes. But this project, this particular CRD4 is focused on packaging, and it's focused on improvement and optimization of the packaging work and getting these devices into the hands of the OEMs, the companies that put these into these final form factors. Okay, and here we're talking about gallium nitride, both on silicon carbide and also on silicon for these areas. Power electronics, I've already mentioned as well, again, part of CRD4, working with our colleagues there. We're looking at developing devices for electric vehicles, charging, for electrification of home, industry, and so on and so forth. And we're looking at not only the development of the epitaxial materials, but also the processing of those materials, and of course, as I mentioned, the packaging. Okay, I want to switch tack here, and you'll understand why I'm doing this in a minute, hopefully. I want to move on to quantum photonics supply chain. So what's happened recently is there's a lot of focus in the last 10 years, and certainly in the last 5 or 6 years, in the UK and Europe, spending billions on quantum technologies, sensors, quantum communications, quantum computing, and so on. But none of the quantum work really would work without photonics. And so therefore, at the Compund Semiconductor Center, we realized with a number of key partners that what we needed in the UK is a photonic supply chain. So rather than looking at custom photonic devices for quantum technology, we would set up a supply chain that can provide almost a sort of off-the-shelf, if you like, photonic components for quantum. So some of the applications here, looking at quantum devices. On the left, you've got quantum-based atomic clocks. On the top, you've got what we would have in a national laboratory, for example, a sort of cesium fountain clock, as they're called, highly accurate clocks. But what we're trying to do is to miniaturize those into something that looks on the bottom left. It is not a quantum atomic clock, but it's what we want to do, like a rack size, router size thing that would fit into, for example, a BT telephone or a fiber cabinet, around phone masts and everywhere really. And these atomic clocks provide high precision timing for terrestrial GPS, for example, that doesn't require satellite, and for example, for financial transactions and so on and so forth. So really important to be able to have these atomic clocks almost everywhere. We're going to have a lot of them. In the middle, you see an example of another type of quantum sensor for magnetoencephalography. So these are highly sensitive magnetic quantum sensors. Now, the middle picture shows, if you like, what is used now in a clinical setting. Not really patient-friendly, very expensive. Uses things called SQUIDs, the superconducting quantum interference devices. They have to be supercooled with hydrogen and nitrogen, sort of, I don't know, a few degrees above absolute zero, and so on and so forth. But what we want to do, you see this child here, University of Nottingham, working extremely hard on using optically pumped magnetometers, which use their quantum sensors, and so we want to move into this area. On the top right, I'm showing a bit tongue-in-cheek a big ship that's cracked. Non-destructive testing is another area that quantum sensors and magnetic sensors can help to identify issues in materials before they're even used in production, but also you can look at aircraft fuselage and so on and so forth. And they have extremely high sensitivity that can pick up the smallest of deformations and and issues in material systems. Right, how am I doing for time? Okay, a minute left. So the reason I'm showing you all of this is because, oh, sorry, one more project. So this is another project we're involved in, which is quantum sensors for scanning batteries. This is for quality monitoring of batteries to go into electric vehicles and so on and so forth. So this is an Innovate UK funded project we're doing with partners in the UK. And this schematic here is showing in the middle an optically pumped magnetometer. And on the left, what I've tried to show you is from one of our reactors. We're developing the wafers that go into the VCSELs, that go into the optical packages, that are the lasers that are interrogating the atomic transitions, if you like, in the vapor cells that you see on the right. So it's a very complex environment. But what we are providing are the optical and photonic elements. These are the partners. So AMTE, AMT are the battery manufacturers. But the reason I'm showing you all that, because as I said, is we've set up this project, a quantum foundry, if you like, for photonic quantum photonic components across the UK. Some key partners there, and we're looking at VCSELs, as I've mentioned, for sensors, for atomic clocks, but also looking at single photon emitters and detectors, which are key for quantum communications, quantum key distribution, and so on and so forth. So having realized this is what we need as a delivery mechanism for almost off-the-shelf, low-cost quantum photonic components, what I'm trying to tell you with this story is that we want to do the same with digital communications. And so the work we're doing now with the cluster with CSconnected is all heading towards, all being well, a digital communications supply chain where we are providing compound semiconductor photonic components for the digital communications market. And so then what that looks like is we're going into the future, looking at providing the lasers and materials for the detectors that end up in what we call transceivers, which, as I showed you in a slide very early on, in a data center, help communication, optical communication between the different computers and servers in a data center, for example, and between data centers and the home, and so on and so forth. So a lot of these optical components can be developed to be used by the digital communications industry, and we are looking forward to, with our partners in the cluster, setting up such a communication supply chain. I'm going to end there. I'm a little bit over time. I do apologize for that. Thank you very much.
Certainly some of the applications you spoke about look and feel quite futuristic, but I think we need to bear in mind that some of that is actually here and now. And as Peter referred to in his discussion before the break, things like quantum dots and other technologies that rely on quantum technologies have been around for a little while, and we're right at the forefront there. So great stuff, and look forward to reading more about what's happening on the quantum side. So really good stuff. Thanks for that, Ali.
Thank you.
And very closely connected, already mentioned that CSC is a joint venture between Cardiff University and IQE. So quite timely to move on to the volume manufacturing, particularly of the epitaxial wafers that feed into some of these application lines that we've already spoken about. So I'd like to introduce Iwan Davies of IQE to talk about what the role is of IQE within the cluster and the activities that are being undertaken. So thank you, Iwan.
Thank you very much, Chris, and good morning to you all. I'm just grabbing 1 minute before noon there, so I think I'm accurate in saying that, and I hope you've had a very stimulating morning thus far, listening to all the partners in the cluster talking about what we can do with compound semiconductors. So as Chris has mentioned, IQE is a compound semiconductor epitaxial wafer manufacturer. So I will tell you all about what's happened in semiconductor wafers. First of all, over the last few decades, a lot of you will be very familiar with silicon semiconductors, which have been around for many decades now, and they're very single element, of course, basic properties, and have been driven by miniaturization, as in Moore's law. And Chris told you all about how the transistors developed over the decades earlier, if you listened to him before the break. Of course, they're very low cost. Moving on to compound semiconductor wafers, these are multiple elements. You've heard about these from Paul and from Peter this morning, how they work in the various devices, and they are very high performance, but also much higher cost. So the way we see this evolving is that there will be a growth in compound semiconductors, but also a growth in an integrated fashion, where we integrate compound semiconductors in a hybrid way with silicon, but also possibly in a monolithic fashion as well. So that's where we see the industry moving in the near future. Now, IQE has been around since 1988 and listed on the London AIM Stock Exchange. Roughly 700 staff globally on 10 sites. We have 4 sites in the UK, and 3 of them here in South Wales. And what we do, excuse me, is we carry out this process called Epitaxy. Now, Peter Smowton mentioned earlier this morning what Epitaxy is, and it's the growth of highly engineered advanced materials on a substrate. You can see on the top right here, many different films, and Peter talked about a VCSEL. That's a good example of an epitaxial wafer where we have hundreds of films, maybe up to 400 films grown on the substrate. And these are grown on tools called MOVPE tools. You can see the white tool down the bottom here. We have 24 of these tools in the Cardiff and Newport plants at IQE. And we also have a lot of characterization tools where we characterize those wafers and ensure they meet the customer's requirements. The bottom left will show the most up-to-date foundry in the group, which is in Newport, called the Mega Epi Foundry. And you can see inside that foundry the clean room in there, where we have currently 10 epitaxial tools. And inside the tools, you can see this photograph here has 15 4-inch wafers, show you what it looks like inside the tool. So just wanted to really explain that IQE is a one-stop shop. IQE's process is solely to deposit these epitaxial layers on the substrate, and therefore our business model is solely that. And we pass on these wafers to our customers in the main, but also, of course, our collaborators. And you've heard from many of them this morning, collaborators in our projects, where they carry out the next steps in the supply chain. And that's chip fabrication, where you pattern, etch, metallize, and package the devices. And then they become components in modules and subsystem systems, etc. And you can see some examples of those in some modern devices. Now, IQE has been around, as I said, since 1988, with quality assured pure play epitaxy. We've been involved with lots of collaborative R&D, many of which I'll talk about later on. Over 35 collaborative R&D projects since 2015 across a number of different project schemes. Again, we'll introduce those later. We do, of course, as Chris suggested, pioneer high volume epitaxy. We qualify globally across all the major regions of the world. And 95 to 97% of our product is exported from the UK. So we manufacture mass scale epi wafers for consumer electronics, such as 3D sensors, for example. You've already heard about that today. So we are the largest 3.5 epi wafer capacity globally, over 300,000 6-inch gallium arsenide wafers and over 100,000 indium phosphide wafers produced annually. And we've got a very long history now, over 25 years, in manufacturing key components like the VCSELs, which you heard about a lot about from Peter, and also Ali in his last talk on indium phosphide lasers, principally in the telecom supply chain. So the drivers for CS technology in the telecommunications market, in the wireless, we find that, for example, over 10 billion chips from IQE's material are powering the smartphone revolution. Over 2 billion photonic chips in the global broadband internet infrastructure from IQE wafers. VCSELs, you heard, as I said just now, a lot from Peter. VCSELs are very, very adaptable to many, many different applications, many of which I show here, but we'll talk a little bit more about those later. And also, you've heard from many speakers this morning about power control. So there are other applications around mobile devices, and connectivity. Again, many speakers have spoken about that. Connected vehicles and safety and security, and more modern applications like things like wearables for health monitoring, the automotive, as you've heard, and also things like Industry 4.0 and the Internet of Things, other photonic applications as well. So the cluster, I know several of the speakers have talked about this in great detail already, so I won't do the same again, but I'll just briefly introduce where everyone sits in the cluster and how it's relevant to the public funding has been made available, and how we are all interacting across the different technology readiness levels. So you can see the entities in the original cluster, Cardiff University and Swansea University, and you heard from Paul this morning about CISM. Those two institutes are operating in the so-called TRL 1 to 3, which is very much R&D and proof of concept. And then moving on to prototyping, you have the Compund Semiconductor Center, and Ali spoke about translational research in the last talk, and Andy this morning talking about the Compund Semiconductor Applications Catapult, which looks more at the packaging and reliability and testing aspects. Again, in that TRL 4 to 6 window. And then the industrials, volume manufacturers, ourselves at IQE, you heard from Richard earlier from SPTS, Newport Wafer Fab, and Microchip, all working in the sort of TRL, the very high TRLs, more towards commercialization. And we supported, of course, in the cluster as well by the Welsh Government and the Cardiff City deal. But the public funding that's largely made available to the universities, of course, is the Engineering and Physical Sciences Research Council, not exclusively, but mainly through that body. But today I'll talk more about the prototyping and the production aspects of funding, and that will be through Innovate UK and the European Commission, as well as I'll introduce the IPCEI on microelectronics later. So first of all, the main project, and many speakers have already talked about this, so again I won't do so in any great detail. Strengthening places, the CSconnected project in strengthening places, and IQE's role principally is in CRD 3.2 as highlighted there, along with all the other partners. And as I showed in the last slide, there were 10 original partners in the cluster. Now we have 2 additional inward investor partners in the form of Rockley Photonics and MicroLink Devices. You'll hear from MicroLink in the next presentation. So IQE's role is pretty much across all the CRD projects. We lead CRD 3.2, which concerns scalability and making larger diameter gallium arsenide-based epitaxial wafers. This will be in the form of 2 strands. One is VCSELs, and again, Peter spoke about VCSELs earlier, and the other strand will be on photovoltaics. Paul talked also about the early stage fabrication of photovoltaics this morning at Swansea, and you will hear more about that from David in the next talk. So that's very much a scalability type work package, focusing on something that we can already do, but we're just making it larger and we're making it more reliable, more reproducible. I won't dwell too much on 3.1, which is what Ali spoke about in the previous talk, where IQE is involved again with a certain aspect of scalability and taking indium phosphide up to 6-inch diameter, 150mm diameters for the same devices that Ali spoke about, principally for communication applications. CRD 3.3, again, Richard spoke this morning, as did Ali just now, and IQE is involved in providing epi wafers in gallium arsenide and indium phosphide and gallium nitride for allowing SPTS to develop their edge processes in their tool sets. But also we were involved with SPTS on some cutting edge development on new materials. And you heard something about new materials this morning from for example, Paul at Swansea. We're working on a rare earth oxide material with ultimate applications in filters for RF. And finally, we are involved in some supply of gallium nitride into CRD4. So a typical supply chain then in the Strength in Places project starts off with the specification of what we need to do. We design the epitaxy, and then we grow the epitaxial growth in green. You can see fabrication, where Peter spoke about the fabrication aspects this morning at Cardiff for a VCSEL, for example. You can see down here, this is a fabricated VCSEL. Packaging, microchip, and the Catapult will be involved in that aspect. And finally, characterization and test, reliability testing. So you can see the companies within the consortium, or the cluster in this case, involved in various steps in that chain for VCSELs, and also examples of what actually is carried out at those steps, the epitaxy, you can see the wafers there, the fabricated VCSEL device, a packaged device, and then finally the testing equipment. And I want to say something very briefly about the applications for VCSELs in the first instance. 3D sensing is a really common one. You'll see, you will all have smartphones, I'm sure by now, where you have sensors in the smartphone looking at things like facial recognition. Optical fiber comms is also a really popular one. And then something slightly more niche, hitherto been niche, is in infrared heating. And these things, they sort of replace halogen heaters, for example, much more addressable and much more efficient. And then in the PV world, the aim in Strength in Places is to produce flexible photovoltaic cells, and they will find themselves on, for example, as you can see in the other photograph there, the wings of unmanned aircraft and so on. And I'm not going to say too much about that because David will talk about that in the next presentation. Just a few examples then of other projects that IQE has been involved with. Very, very briefly, Ali did mention quantum technologies projects. This is a huge initiative in the UK at the moment through Innovate UK. IQE has been involved in one called Aquasec, which concerns quantum cryptography in the form of quantum key distribution devices. These allow safe and secure communications which are resistant to an attack by, for example, a quantum computer. Now, you may well hear about these in the news and have done so recently. So quantum key distribution prevents eavesdropping effectively on secure communications. And this, of course, could be in banking, in commercial, in healthcare, and so on. So many different applications for this. And the key aspect of this project is to make sure we are able to mass manufacture such devices in a much more miniaturized form. So you've heard a lot about miniaturization this morning at a reduced cost, of course, and to give ourselves a sovereign component supply chain in this activity. And you can see the project team is very much a national team with universities and UK companies and so on the right-hand side. And then SPIDAR is another quantum technologies project which is focusing on LiDAR, and you heard about LiDAR from several speakers already this morning. This one will be focused on long wavelength LiDAR, which is in the eye-safe region at 1550 nanometers and above. And this project will be looking at the environmental monitoring for autonomous vehicles, for example, and will be able to allow for longer range operation with a reduced solar background at those higher wavelengths, improving the noise and performance, and allowing operations through obscurance such as smoke and fog, for example. So again, IQE will be involved in this project through single photon detectors and quantum emitters, which you've also heard about already from some other speakers. And again, the supply chain is very much spread across the UK. I'm not going to say too much about Quantum Foundry, as Ali introduced this one, earlier. IQE is also involved with that, principally through single photon detectors and quantum light emitters. So I'll move on then to European projects. IQE is very much involved in European projects, and many of you might have heard of Horizon 2020, which was the last framework program in Europe, 7-year framework program, which is now turned over to Horizon Europe for the next 7 years. This particular project called CHIP AI is a Horizon 2020 project where IQE provides resonant tunneling diodes, nano photodetectors, and nano lasers, which are going to be fabricated into use as chips for neuromorphic nanophotonic chips for artificial intelligence systems. So again, we are involved with several universities in the UK, as well as European universities and companies such as IBM. Finally, I'm going to talk about the other end of the scale, which is really very high TRL project. And this is the important project of common European interest on microelectronics, which is the very first of its kind, the very first IPCEI. There have been other ones since, but this is the first one. And this was the founding countries were Germany, France, Italy, and the United Kingdom. And this is a consortium forming a very large project, 7.5 billion euros. And the key aspect of the IPCEI is the so-called first industrial deployment. So this allows all the partners in the project to access funding for carrying out very high TRL work, which is immediately pre-commercialization. And this then does not contravene state aid rules. So this is effectively something that the European Commission has been working on to allow European companies to become more competitive on a global scale. Now we can see the top left here that there are 5 strands to the IPCEI on microelectronics, and IQE is involved in strand number 5, and we actually lead that strand, and that's on compound materials. And if you note, we also have in that strand Newport Wafer Fab and SPTS. So we have 3 South Wales cluster partners in a very large pan-European project at very high TRL. It's important, though, that we have a lot of underlying RD&I, so research, development, and innovation projects. And that's really where Strengthening Places, for example, plays a very crucial part, as well as projects carried out at the universities. Now, many of the other partners in the cluster are so-called associated partners of the IPCEI and allow us to carry out very important underlying research and development that feed into this pipeline at very high TRL. Also, there are a number of activities within the IPCEI, something called Spillover, which aims to spread the word about the technology, for example, through workshops and things called techathons, if you've come across those, in non-IPCEI core countries. So effectively spreading the gospel at a much wider outreach level throughout the rest of Europe. Okay, well, I thank you for your attention this morning, and hopefully you've understood what IQE's been about.
Thank you very much, Ewan. I'm sure we can test that when we hand the test papers out at the end of the session. And I think it gives a really good overview of the scope of the semiconductor world and the compound semiconductor world in particular. And one of the questions that cropped up, we may need to foreshorten the panel session at the end, the Q&A, but one question that popped up was about the technologies that are involved and the markets that are pulling on the epitaxial wafer supply. And I think you covered that quite well when you touched on VCSELs and so on, largely driven by sensors right now, but in the future it will be other sensing applications and and areas such as, say, healthcare sensing, connectivity, and of course, energy, whether it's power electronics that we've heard a lot about, or generating energy, which leads in very nicely to our last speaker of this session. So thanks, Ewan. And I would like to now introduce David from MicroLink. David Rees will be telling us about the role of MicroLink, who is a relative newcomer. I mentioned that a number of the companies within the cluster have been around for the last 30 or 40 years. So MicroLink has joined in the last 2 or 3 years, I guess, and been a very active partner in the Strength in Places. So I'd like to introduce David. Thank you.
Thank you, Chris. Good afternoon, everyone. I will share a short presentation with you. The emphasis of my presentation is more, you've had a very detailed look today at the technologies and how they've evolved over time, and how you're going from chip level up to ultimately they're going to be high value manufactured products. My emphasis is very much at the rear of that process, where we're taking technologies, we're taking product, we're taking capabilities from IQE and other partners, we're integrating them, and we're offering them into specific end user platforms over time. My role is to develop the manufacturing and process capability in South Wales. I'm employee number 1. I joined the company in February, and I'd like to take you into my presentation. So I'll take you on a brief journey, explain about the company, our origins, our offer, our evolution over time, where we see our competitive advantage, where we see our road ahead over time in terms of how we're going to utilize these technologies and grow the business and grow value for our customers and ourselves. So the company originated in the US in 2000. A number of processes will evolve for communications technologies, but also for solar energy harvesting. MicroLink UK was set up in 2019 because of some difficulties, as you might imagine, in the current situation. Progress has been slowed, but our role is to design, develop, and manufacture advanced solar arrays for aerospace applications. We've got a core competence in epitaxy, but as we grow and as we need to grow our production capability over time, we'll be looking to utilize the capabilities of IQE, Newport Wafer Fab, and others within the cluster to allow us to ramp to high volumes of manufacture. So these are examples of our arrays. I'm not going to spend too much time explaining their functionality in detail. The key elements you have to understand is where you look at the specific power. Particularly for aerospace applications, they're sensitive about every single gram that you're going to put onto the aircraft. So the key differentiator for our product is the amount of energy we can provide for the solar powered platform for the lowest mass. If you want to see a more detailed view of our epitaxy process, please look at our website. There's a link at the top of the slide. This is our evolution over time. There are a number of competing technologies utilizing entirely different chemistry. The vast majority of you will be probably have some device, possibly something in your own back garden that is solar powered on a silicon-based technology. We're using a gallium arsenide-based technology, so-called triple junction, allows us to harvest light at 3 different frequencies in the spectrum, everything from the visible light range down to some ranges in infrared. That allows us to have an efficiency in the 30-something odd percent based on our AM0 measurement scale, which is a known standard for the evaluation of solar efficiency devices. Where do we need to be over time? If we're going to maintain our position in the marketplace, if we're going to be able to become the dominant design in the marketplace, we have to focus upon evolving further efficiencies at lower masses. So here's our process evolution. This is our story. This is why we're in South Wales. Our current capability, we're in approximately the 40 kilowatt scale out of our facility in Chicago. So for pre-production platforms, for prototyping, that's perfectly capable. But if demand grows in the fashion that we anticipate it will, then we need to have to go at some considerable scale, some significant higher manufacturing scale in the megawatt range per annum. We have our own ELO, inverted metamorphic process for junction 3, which is proprietary, and we're going to maintain that. But as I'd explained, we will evolve capabilities with our supply chain partners. The reason the facility is in South Wales is very much because of CSconnected. It's because of the investment made by UK government, Welsh government, to evolve a cluster dedicated to compound semiconductors and to grow the economy from everything from device level up to complex machines. So we're probably associated with CSconnected. We're involved in strategic places with our friends at Cardiff University, Swansea University. We've involvement with the compound semiconductor applications with a program called LUS, where we're utilizing, we're developing a device that will emit light at a particular frequency and to use that to disinfect common touch surfaces as part of a counter COVID measure that's under development at this time. So who are our target markets? High altitude pseudo satellites. So effectively these are solar powered aircraft. They climb to approximately twice the altitude of commercial aircraft. They sit there and they use the sensing platforms or they use as communication platforms. So for sensing platforms, it may be for mapping, for weather, for directing. A particular example that could be utilized is in the event of a natural disaster, you can have a persistent presence above that operation, and you can be utilized as a communications platform and a sensing platform to inform those programs. Where, because of the lightweight nature of our product, it also lends itself to the newer generations of satellites, particularly CubeSats, where again, there very much is a focus upon a low mass solution. The extant capabilities are heavy. They require glass protection to protect them from radiation in space. And in fact, anywhere where high performance, low mass is of value, in sensing platforms, communication platforms, those are our target markets in the immediate future. The early adopters have been for HAPS and for solar powered aircraft, and we're providing prototype and pre-production capability to the key platforms that are currently operational. The world record for continuous flight is held by Airbus for 26 days. Our cells are used on that platform, and we're part of that world record attempt. So what's our road ahead? You know, what's the future for MicroLink devices in South Wales? As I've stated, we're going to have to jump. It's a considerable leap to go from a kilowatt scale to a multi-megawatt scale manufacturing facility. We're going to have to continue to evolve the efficiencies in both our manufacturing processes and the capabilities of our product over time. And our goal for the fourth bullet, as you can see, we want to take an unassailable lead in low mass, high efficiency solar power products and systems. We understand that at this stage, our customers, those that are making HAPS platforms, they tend to be very vertically integrated. They tend to acquire a lot of componentry themselves to assemble it into subsystems and then integrate it into their platform. We're confident that their model will change over time. They'll be looking for their tier one suppliers to provide more value add and to be looking at systems capability in totality. So our roadmap will involve not just the cells and the arrays themselves. It's going to be how we offer systems with the complete power harvesting and power storing, power management for those platforms as an integrated offer to that space. Thank you for the attention. I'm thankful for Iwan. He stole a lot of my thunder with regard to our involvement with CSconnected and the cluster's capability, but he did a far more eloquent job than I ever could. Thank you, everyone.
Thank you very much, David, and also to all of our speakers today. I do apologise, I've not done a great job on sharing, so we're pretty much up to the time limit. But I think we've answered most of the questions that cropped up or may even crop up as we've gone along. Hopefully the main messaging coming out of today is that we do have a very strong industry sector, but at all levels, not just at industry, from research and development through prototyping all the way through to high volume manufacturing capabilities here in Wales. And in fact, MIT identified one of the key strengths of the region of Wales is compound semiconductors as a worldwide presence. So I guess the question now, and the question I would have put to the panel, is what are the challenges in maintaining and growing that position? But hopefully we'll be able to come back to that in this afternoon's session. We are reconvening at 2 p.m. for a relatively short session, and that's really concentrating on the education sector, looking at what the cluster means to the Welsh economy and also what it means for jobs and career opportunities. And we'll be hearing from both Cardiff and Swansea universities about the education facilities that are available all the way to graduate and postgraduate level. So that's something to look forward to this afternoon. Starting again at 2 p.m. Apologies, we run out of time for the for a Q&A session or for any meaningful Q&A session, but I think we have addressed, as I say, a lot of the questions as we've gone along. So thanks very much. I'd like to extend my thanks to Wales Tech Week, to Georgia for driving the presentations and the session, and to my colleagues Camille and Jesse for pulling the sessions together for the day, and look forward to rejoining you at 2 p.m. So we can grab some refreshments and get back together a little later. Thank you very much.
Thank you for watching. Rewatch all of our sessions online. Thank you to our partners.